All right, today we are going to take the logistic model as an example and try to build it from scratch, kind of have the skeleton on how you build differential equations from scratch. There are three basic ideas that you have to keep in mind when you build a model. One is the physical law, such as the law of conservation of population or conservation of energy or whatever, Newton's law. And then the second one is the experimental fact, such as the force of gravity on a body is proportional to its mass. And then we're going to glue these two together with calculus, okay? So that's how we go about building these models. So for our logistic model, one experimental fact is we're going to assume, we are assuming here that the number of individuals that are born per unit time. So it's almost, this is a rate of change, right? It's almost like saying, without saying, it's dp dt equals 0, right? So per unit time, what's the number of individuals that are born, okay? That expression is proportional to P, okay? Sorry, is proportional to P. And the other one is similar. The number of individuals that die, let me just point, that die per unit time is proportional to P squared, as we explained the other day. Talks about the population of fish eating fish, and for a law of large numbers, P squared is much bigger than P. So that's how the P squared came about, if you remember. And we're going to denote that constants of proportionality. S, the first one, we're going to call it A. Most books call it K. I just called it A. So now we're gonna try to put this two pieces together. So in here, it says over a period of time called delta t, what is the change in the population? That's what it says, right? What's the change in the population over this period of time? And that change has to be the growth, the population. Here is the population per unit time, because we are only dealing with a unit time here. What's the growth rate times that population over that period of time? And we're going to take away the death rates over that population. In our case, it's P squared over that period of time. So that should make sense to you. So I basically rewrote this and I changed KB, KD, constants of death, and called it S, and constants of birth, called it A. It's nothing to it. And then I divided both sides by delta T. Okay? So this expression should remind you of the difference quotient, right? F of x minus f of y over x minus y, or f of x plus h minus f of x over h. It's just a slope. It's a difference quotient. It's an average rate, okay? So what are we going to do? We're going to take limits on both sides. We're going to force the time to shrink to 0. So we look for the instantaneous rates of change. So this is the average rates of change. And if I take limits of this left-hand side, this is how we do it in mathematics. So when you see LHS, it just means left-hand side. We're going to take limits as delta t goes to 0 of the right-hand side. This is the right-hand side. I was just being lazy. I didn't want to write the whole thing again. Okay? So recall the definition of derivative. This is the average rate of change, right? And if you take limits, it becomes the instantaneous rate of change, which is just the derivative. And I wrote it in two ways. So that means the left-hand side is just dp dt, right? That's your left-hand side. It's this expression here. This is dp dt, okay? And the right-hand side, the delta t cancels. So before you take a limit, cancel delta t from both sides, from both pieces. because these are not factors. You've got to factor out delta t and cancel. And you're going to get AP of t minus SP squared of t, which is just that. Feel free to write this. Okay? And basically, that is the model we came up with twice. And we did it for the third time today. So this is the logistic model. Recall, it is not linear. It's solvable, but it's not linear. Okay? So, here is your quick assignments for Monday. I would like you to, and I would love for you to work in small groups and their discussions. I would like you to build the spring system model. And this is how it looks. Sometimes you see it written this way. Okay, so when you see x double prime, it just means second derivative of x with respect to t. Same thing when you see x. Did I say prime? I meant two dots. If you see a one dot, it just means dx dt. So these are abbreviations. X triple dot is that, and so on and so forth, okay? Same thing here. Theta double dots is just d squared theta dt squared, and so on and so forth. So this is the model that represents a spring system. This is the one for the pendulum. We talked about this briefly on the first presentation. We said that this is nonlinear, right? Because of sine theta. This is not a linear operator. And the way we're going to solve it, again, we don't have to solve it. We could use the qualitative approach to draw conclusions. But I would like you to build these models and solve them. So for the first one, it is linear. So just try to solve it in your respective groups. And this one is hard. It's nonlinear. What I would like you to do is to assume theta is very, very small. This is how you write theta very small. You do like a less than, twice less than one, kind of. It just means theta is small. That's so if you have a pendulum, okay. Actually, I can do this. All right. So if you have a pendulum, and this is L, this is the length of the string, and the pendulum is swinging back and forth. So this is your L. Oops, I erased my own function. Okay, so d squared theta dt squared plus sine theta g, I believe g. I think there's an L here, there is a g here, equals 0. I hope I didn't mess up. So that's your length of the string. This is your theta. And the gravitational force, G, 9.8 meters per second squared, or 32 feet per second squared. Sometimes you see 10 meters per second squared. It depends on actually the location, where you are in the world. Okay, so you could use 10 or use 32 feet per second. So these three letters, for instance, L, G, and theta, represent, this is the length of the string, this is theta, and G is the gravitational force. So the second model is nonlinear, but I would like you to do is to replace theta. We're going to assume theta is small. In other words, we're going to let the pendulum swing like from here to here, where theta is extremely small, so that we can replace sine theta I'm being okay. So you may remember from calculus that when theta approaches 0, sine theta over theta gives me 1, right? You can also say it this way. Limits as theta goes to 0 of sine theta equals theta, which means when theta is very, very small, sine theta is approximately theta. So we're going to go to this differential equation, and we're going to replace sine theta by theta to make the ODE linear, and then try to solve it. That's what I'm trying to say here, okay? So give it a try, and I will talk with you later. Bye-bye.